In this demo, we are presenting a training and evaluation environment that we built for a problem we're tackling together with the German Federal Office for Radiation Protection. Aerial coverage path planning in nuclear emergencies. First, we'll introduce and motivate our task, outlining it at a high level. Then we'll dive into the details by setting up the simulation, defining the task more precisely, and breaking it down into sub-objectives. We'll also highlight what makes the problem we're tackling unique. Finally, a significant part of our demonstration will focus on presenting examples in various environments to illustrate the complexity and novelty of our problem. This work does not present a final solution to the problem, so do not expect perfect paths. Reliable energy sources are essential for a sustainable future. Nuclear power provides a reliable, low-carbon energy source, but the risks of reactor failures and potential disasters highlight the need for strong emergency response measures. This is the explosion of the Fukushima nuclear power plant from 2011. But of course there are also other scenarios that might lead to radiation risks. Like the explosion of an atom bomb. So, after radioactive contamination incidents, we want to create a map of how radiated everything in the area is. This can be done with helicopters or UAVs that collect two types of radiation data. First, the local dose rate, which is the radiation intensity that is arriving at the aircraft. And secondly, the ground radiation level, which is self-explanatory. Our goal then is to generate a detailed radiation map while minimizing exposure. So, in other words, we want to fly over every point in a given area of interest to find out what the ground radiation level is. And we do not want to fly over points where the local dose rate, so radiation intensity at the helicopter, is too high. The critical issue is that the local dose rate is only known at the current time and position of the helicopter. This is the task on a high level. On a more detailed level, it can be described using the following reward function, which is the weighted sum of R1 to R5. R1 is just what we talked about. We have to maximize the surveyed area. But now there's the additional condition that we have to stay at an optimal altitude of 90 meters above the ground. R2 is also what we talked about. We have to adhere to radiation limits. R3 is something completely new. We have to minimize the amount of turns. This is because in curves, the helicopter is tilted and so are the measurement devices, which leads to worse measurement quality. Furthermore, we have to minimize flight duration, which just makes sense, and ensure that the helicopter returns to the base within the specified time frame. This could be, for example, because of fuel limits. Now that we have defined the task, let's have a look at the simulation environment we built to train and evaluate policies that aim to solve it. The point cloud represents the terrain, with the orange line showing the helicopter's flight path. Red dots indicate measurements taken. Black dots mean we want to measure that, but haven't done so yet. The measurement area depends on a cone pointing downwards from the helicopter, so the size of the measured area changes with altitude. At lower altitudes, the area is smaller. At higher altitude, it broadens. However, measurement quality decreases above 90 meters. The Inferno color mapping shows radiation levels at the ground sourced from state-of-the-art simulations provided by the Federal Office for Radiation Protection. We received too few simulations for generalization, so we augmented the existing ones using image transformations to create a larger, more diverse dataset. DECGL is used for visualization, which comes in handy when we want to see our data on a 3D map. So when our agent flies towards a radiated area, it does not see the radiation map we see, It only perceives the local dose rate, which we can see in the bottom left corner. And it gets higher and higher, and now we should turn around because it's getting dangerously high. Our task is a coverage path planning problem. It is particularly similar to a CPP in unknown environments, but finds its use in autonomous vacuum navigation. However, there are a couple of key differences. Firstly, radiation avoidance relies on local dose rate gradients and not on strict boundaries. Secondly, we're operating in a 3D environment where we have to maintain an optimal altitude. And last but not least, we have to minimize turns. Let's have a look at different example policies we trained using reinforcement learning in order to highlight the different complexities of our task. First, in a flat environment. In this scenario without radiation, the reward function was simply defined by the amount of newly measured points at each step. The issue of the resulting policy is that we have too many turns and that the unmeasured area gets fragmented, which leads to longer flight times. This is because punishment for fragmentation is given too far in the future. This can be addressed by using the total variance reward from the paper proposed by Jonat and co-authors at last year's ICML. By adding the difference of border length of the measured area before and after, we get a policy that performs better. However, there are still too many turns. Now, let's add radiation and see how this affects our path. The uncertainty the radiation introduces leads to a path with way too many turns. This has to be addressed using another reward term. Also, radiation is avoided, but a little bit too much. It would be nicer to go a little bit closer to it. Especially because highly radiated areas are particularly interesting. Let's reintroduce punishment for too many turns. This leads to a better path, but it's still not perfect. We have less turns, but still too many. We do avoid radiation, but not always, as you can see indicated by the green dots in the end. And we could choose a path that covers the whole area of interest faster. We just covered Berlin. Our problem gets more complicated when we move into mountainous regions. This is because of the condition that we have to measure 90 meters above the ground. In mountainous regions like this one, our agent has to survey the whole area, or as much as possible, while adhering to the flight constraints of the aircraft. This leads to sparse rewards, policy stagnation, and in the end to a suboptimal policy. Finding a policy that solves our problem in such complex environments remains part of future research. We hope you now have a clearer understanding of the aerial coverage path planning problem in nuclear emergencies, including its complexities and the environment we have built to train and evaluate policies for it. Thanks for watching.